Yeah. As you know, I'm Arunachalaeshwaran, and so I'll be giving my talk on cryptography and like an introduction to it. So first, initially, I'll be giving some like basic discussion kind of thing we'll be having, and then I will just give you a few kind of like a toy version of the problems we deal with in our research, so that you get a good feel for the subject. And then I will be explaining some of the common techniques that is used, how it relates to other fields in theoretical cryptography and things like that, as well as how connections with mathematics and things like that, and what are the problem areas and things like that. So this is what I will be doing. Okay, so for the discussion, like when you think of cryptography, like what are the like words or phrases that come to your mind? Any like encryption, passwords, then privacy and things like yeah. So as you know, like you guys have somewhat of a good understanding. Like cryptography is about these things, but not only these kinds of things, but there are also other things as well. Like I will be showing you some things like multi-party computation and things like that. I'll be going to that later. Uh, so okay. So if and I would presume most of you would have heard of applications of cryptography like using HTTPS and many like credit card security, ATMs, cryptocurrencies, and so many other things. So let me start with something much simpler. Say for example, you want to okay. So this is like a common setup for the problem. There is like one party called Alice, we'll just denote by A, and there is another party called Bob, and they want to communicate with each other, right? But there is some an eavesdropper, Eve. I'll just denote by Eve. Now they want to send messages between each other. But eavesdropper should not be knowing it. So this is like a very simple problem. Say for example, is this visible if I write it at top there? Okay. Say for example, Alice wants to send to Bob 011. He has to like she has to like encrypt it and send it to Bob. Can you guys think of like a very simple encryption scheme for this purpose? But even if once the scheme, the whatever scheme you come up with, it will also be known to you, right? The scheme will be known to you, okay? Like if there is some kind of secret key and things like that, that won't be known to you. So like you can easily reverse it. Just break into the packets and bring some offset and then send in different action states. This is yeah, but like how do you do that offset? By a secret cipher. Is that some cipher? Secret cipher. Okay, I'm not sure what that is. Can you describe me more detail? A cipher which is defined over any span. Okay. Yeah. Okay. Yeah. Any other things? What's that? A pre-decided key which only Alice and Bob. Yeah. Yes, that is one thing. Yeah, that's like one part of the solution. But how do you use that? Like something like add 102 is and then yeah, I think you guys have seen the idea. Okay, I'll just give it. Say for example, Alice and Bob have this pre-agreed key, and you know the key as let's say 101. Right? Now, if they want to send the message 011, what they will do is they will do this XOR. So the ciphertext C is equal to M XOR of K. So in this case, message M is like 011. So when we XOR it, like what do we get? 110. Yeah, 110. Right. So this is the cipher that would be sent out. This is like a very simple scheme, but this is like the main concept which is used behind the design of other ciphers. It is assumed Dom has the key. So now once Bob has the key, again, like to get back to the original message, he can again XOR it with the same key, and he will be getting that. So this is like the one-time pad. So this is very something very common use, but there are like some flaws in it, right? Like say for example, if I want to send two messages, if I send it the second time, let's say my second message is 110, uh, and I'm using the same key and sending it. Now, if I actually let's say the first cipher is send is C1 and second cipher is C2. Now, if I do C1 XOR C2, it will equal M1 XOR M2, right? The case cancel out. But this is like revealing information. Can you see about this somewhat more than yeah. So this kind of thing where there is like absolutely no information getting leaked. This kind of thing is called information theoretic security and things like that. But the downside with this is like if you are having something like this, information theoretic security, it's actually technically called perfect secrecy, like Claude Shannon, if you know about him, defined it in like the 1950s or so. If you are having something like this, the key size should be as long as the message, basically. This is like a huge disadvantage because the key you have to already send. Instead of sending the key, you have sent the message itself, kind of, right? So this is like one disadvantage of this kind of perfect scheme. So we will be like relaxing it a bit uh, to proceed further. But before that, I would also want to add something. Yeah. There are also something called key exchange protocols. These are like a way to exchange this key, right? And in the classical setting, there are like they are based on computational assumptions. I'll come to it later. But in the quantum setting, there is actually a way of exchanging, doing this key exchange, uh, and without even agreeing on the previous things and all. That is like one of the reasons why quantum computation is also very interesting and how it relates to cryptography. I won't be getting too much into quantum in today, but that's it. So next thing is like I'll come to is computational version of this. Okay, so for example, the problem was the key length was as long as the message, right? So what we want to do is we want to apply a function. This function is called the pseudo random generator function, right? And it's a function will be denoted by f. So now whenever we have say f of some x, let's say x is a n bit string, it will let's say extend it to uh, y. This is like more than n bits. Yeah. So there is like this PRG. Usually, it's based on something called indistinguishable. I will come to that what it means. So the goal is this. So we once we get right, it like one of the simple ways you can think of is like x. I will just add some zeros. It will be more than that. That's like simple thing, but that's not going to be very useful, right? So the point is that this y should also be looking like a uniform pyramid to assess someone. You guys know about the algorithms and polynomial time algorithms and things like that, right? Okay. So now let's say there is an adversary. Usually in cryptography, we deal with someone adversary. Adversary is someone who's like trying to break the security of the system which we are making. So let's say this adversary has like a polynomial time computation capability. You can run any polynomial time. So now the point is that let's say this n bits. I'm just saying it equals n bits. Yeah. Okay. So greater than n bits. This is like n bit string. So now I'll explain what this notation means. First, u of m means that we are drawing a uniformly random string of n m bits. Similarly, here also a uniformly random string of n bits. And now we apply a function of f on that uh, un. And now these two things should be looking indistinguishable. And by indistinguishable, I mean here that this adversary A If he's using a polynomial time algorithm, he won't be able to guess if it is from this one or this one. Like, say we sample with probability say 50% from this and 50% from this. And ask the adversary to guess whether we have drawn from this one or this one. He won't be succeeding with probability less than half plus negligible function. For now, you don't have to worry what the negligible function properly is. I'll give a brief. It's not too important though. Okay. I'll first explain this lambda. No? The lambda is like a security parameter. You guys have heard of like AES 128 or RSA 4096, have you? Okay. I mean, even like you haven't seen like any simple example or in the browser and on your web browser also you haven't seen of AES of 128. Yeah. Yeah. Have you seen this movie 128 or some other number following it? In laptop, we do have for Wi-Fi settings AES IP. Yes, yeah, it's something like that. But have you seen this parameter 128 or no? Okay, fair. This kind of thing is like in ISA 256. Yeah, yeah, yeah. So that kind of thing. So yeah, that number is like the security parameter. It basically says how many bits I have to guess in essence to break it. It's something like that. Okay, there is more formal definition of it, which I will not go. And there's negligible of that means essentially like this negligible function is something like a log. It's like a something which is smaller than a polynomial. So it will be like something like 1/2 to the n, right? This 1/2 to the n, it's like smaller than any 1/, polynomial of it, right? Polynomial or rational function. Eventually, asymptotic here. It's something like this. This is what a negligible function. You don't have to worry too much about the detailed problem. You can read about that later. So yeah. So now once we have this way extending it, can you see how to modify the scheme to achieve it like with the smaller p? We give you the like the reason we started was like k was small. Oh sorry, k was as long as the message. So now we have a way of extending it, right? So now can you see how to use that extension and solve this? Yeah, I guess I will give you the answer. Say for example, okay, yeah. Say we are having like 2 bits first. Yeah, let's say the TRGF extends from 2 bits to 3 bits. So instead of taking the k as like 3 bits itself, we just take let's say I'll just say call it q and I'll just take it as 2 bits, say 1 1. And now I apply f on it. So f of u, this will be giving me something like let's say it gives me 101. Right? So it will extend it, right? And now if I XOR it with it, this kind of problem goes away. Yeah. Is this correct? So is this kind of clear? Or so this is like encryption and things like that. So okay, now I'll come from a slightly different kind of problem. These are groups, right? Finite cyclic groups and things like that. Okay, then I'll explain what are finite cyclic ripples. Uh, I'll just give a, like an abstract version for it, for it, so it's simple. So we have something called a generator G, right? So now we can do the operations like G, we can like square it, cube it, and so on. We can arise it to any power really. So all the way up to G to the n. So whenever we do something like this, we'll be getting like a new element of a group. And eventually what will happen is after some time, we'll just return back to the original. Rather than the original, I should say we should take will technically be written to the identity element of the group. Identity element is such that like E times G, it will be like equal to G, or rather any X really. Yes. Whatever we multiply this E with, E is the identity, so it's like a multiplicative identity, like one. So it's yeah, you'll be getting. So this is what like a cyclic group is. Right, so the now finite cyclic group is. So now the problem is, now say for example, we are given a group element, let's call it Y, right? And now I want to find G to the, let's say P, or I have to find this such that G to the R is equal to this element Y. Now this is, actually it turns out like finding this R is like very difficult. If you are given just this Y and G, finding this R is extremely normally means like you can if it's like over real numbers or something like that, you can take the logarithm and do some division and get it. But in a over a group, it's very difficult. This in cryptography we make lots of these assumptions. There's no formal proof that this is like hard, but like people have tried so much and no one has been able to break it. At least using physical computers, quantum computers can take it. That is another thing. So this is called a discrete log problem. So so now, say for example, one way if you want to like do come up with like an encryption scheme, let's say rather than encryption scheme, I will change it to a bit. I will come to a bit commitment scheme. Now think about the bit commitment scheme is like this. So for example, let's say you want to do a coin toss over your phone with your friend. Right? So how are you going to be able to do that? Because like one of you has to make a call, another one will be making the prediction, and whoever gets it correct like wins. So this is like the thing. But like even on a phone, you can easily cheat, right? So because one person tosses the coin means other person he can just change, say lie what so. So that is basically the problem. So any idea how to solve this? So you want to do a coin toss over the phone with your friend. Like if you say one of the tosses, you can like lie about it, and so you can't get this. So how would you like go about that tossing the coin over the phone such that both of you can agree that it's being done properly? Yeah, but like for that simple like, cryptographic thing, you want to solve it better. So you just say it. You can only talk same words and things like doing multiple tosses and trying to get if this is an actual sequence. Like yeah, but like how do you determine the exact thing? Okay, like okay, I'll give you a hint. Let's say you're doing it, let's say over a person kind of thing. What you can do is like one person will write it in an envelope and keep it in front of. Like the call will be made. Then the other person will toss the coin and say what it is. Then the other person can open the envelope and show what it is, right? So this is like one physical intuition behind this. So what keeping writing something inside the envelope and keeping it, this kind of thing is called a commitment scheme. So now if you are having like a mathematical commitment scheme, you can basically use this over phone as well, right? So that's what we will be doing. So yeah, so we will be building a mathematical commitment scheme based on this GR, this discrete logical assumptions. Yeah. So this commitment scheme is called the Peterson commitment scheme. Uh, so this is how it's going to work. say we want to commit the message M. Yeah. So so now this G will be known to both the parties. That's not a problem. But say there is this person who's like committing, and there is the other party, like me, just say the whoever decides the toss or something. There is DL just have it. So what the commitments we are sending is, we are essentially sending this G, M, G to the S. This S is like randomly chosen. Yeah, so basically this group, can you see like the number of elements? Let's say if it's M means like this S will be chosen from like 1 to M uniformly or something. So, right? So yeah, so this is like the commitments. Okay. So we first send over the commitment to D. So this goes to D, right? Now D will like toss a coin and send the result. Let's say the coin toss result is B, like B, and B is sent over. Yeah. So now the committer will like open the envelope and reveal what were the messages. Now, because the committer was the one who chose S, he knows what S is. So what he will basically be giving out M and yes will be sent. Mhm. This your party and D will verify that whether G to the M, G to the S, whether it is equal to the, let's call this whatever originally comes in as let's say let's call it like it's equal to Z or not. You will check whether this happens. If this happens means like we know that C is not lying, right? Okay. Now now notice like a few things. Firstly, just from looking at this Z, he has no idea what M is, right? That's kind of clear, right? Because multiplying by G to the S, this is like completely random thing. Multiplying by that, you have no idea about what that is. So this property is called hiding property because we have no idea about it. Now, now the C can cheat as well, right? Like we can first send one M and then later change it to something else. So we don't want that to. For that property is called binding property, which is what we want to achieve. The scheme achieves that because, like, say for example, he wants to say it's change from some from M to some M prime he wants to go to. So then what he must do is he must find something level which satisfies this equation. Something that satisfies this equation. Right. You actually found this thing. I will just rewrite it as g to the s prime equal to z to the okay z over g to the n prime. Can you see this is basically like the discrete log problem? This value he has, but finding that this is like very hard problem as I told you. So he won't be able to do this. Can you see this? So yeah, so this is like the binding property, and so this is how this particular schema starts.
But you can just switch, swap M and S and then in the opposite order.
Oh, we could technically do that, yeah. So yeah, I think this should be technically simplify this thing towards it. It should be technically H and C similar. So yeah. So like okay, so now you guys have this at least for the intuition for this commitment schemes, right? Like having it in an envelope and revealing it. So we can do something called a zero knowledge group based on this. How do we ensure the value that we get that? That is the correct one. That is, what like we check this equation, right? Yeah, the point was like how do we ensure that, okay, that is exactly what was received? What do you mean by the m was not changed, is it? That's, yeah. So we check this equation. The h. We're checking this, right? This is that we got in the first round when we basically places the envelope on the table. That and in the end he reveals this M and S. Once he reveals M and S, this G and H are like public. We know it from the start. So we can basically check whether this equation holds or not. This equation holds, we know that the value of M is like less than can be solved. The bit B that was sent back. How do we ensure that that is? I mean, that's just like a 0 or 1, right? That's like a that's no, that's basically like the big B is like the call, whether it's a head or a tail. So that's it. So that's like public. Both of them know it's very simple. It's just head or tail. There's nothing to change there. What role does the bit actually play? I mean, that's like the player calling, right? Like this M is like the result of the context. You toss it, and instead of revealing M directly, you just commit it and send it. So now the other player will call it. The call is known to both publicly, right? And then now the way only way it cheats is like if he changes this result. If we can't change it, means it's fine. So now he can't change the result. Right? You said something about it was like it was okay. So I'll come to something called zero knowledge proof. Uh, right. So this is like one of the most interesting areas in cryptography. So in zero knowledge proof, this is like okay. So there will be like a prover and there will be a verifier. So now the goal of the prover is to convince the verifier that he knows something. Right? But he could give like a traditional mathematical proof or something like that to him. But the problem with that is he will reveal like what it is. For example, let's say this. Let's even take this discrete log. So z is equal to g to the r. So now both of them know this z or slide it below. This is like the problem instance z, and also both of them know g. Right? Now P wants to convince B that he knows this one. He could directly send that. That is like one way of convincing B. But if he does send it directly, the B will also come to know what that R is. You know how he can do this kind of thing without actually revealing it. So now this is kind of the goal of zero knowledge proof. For this particular problem, there is something called the Schnorr protocol. I don't want to go into too much detail in it. It's also somewhat similar to the commitment scheme thing you saw before. So in this thing, what we do is, yeah, okay. So the idea is essentially this. I will give a zero knowledge proof of something else, but because we want to also show this. So you guys have heard of the graph coloring problem. I'll just explain the problem. No, I have no issue. See, for example, we are given some graph, and it's technically a planar graph. Planar graph means like there will be like no overlapping edges. Like for example, edges like this won't be there. These things overlap, correct? And we draw it this. So this is what a planar graph is. And it actually turns out a planar graph can always be colored with four colors. And coloring here I mean is that each vertex will be associating a color such that no two adjacent nodes have the same color. So like if it can always be colored with four. Checking whether it can be colored with one is actually pretty simple. Like if there are no edges, then it can be colored in one. Two is also quite simple only. It's like bipartite checking, same thing as that. So you can do it. Whether it can be colored with three colors or not, this is actually a very difficult problem. I'm not sure how many of you have heard it. Like this is one of the NP problems. It is fine if you don't understand what NP complete is for now. I'll come to that later. But yeah, so it's like a very important class of problems. So there are so many problems such that if you like solve one of them, you are essentially like solve all of them actually. These kinds of problems go across so many fields. Like they are in like circuit design, they come in mathematics, in combinatorics, game theory. Pretty much whatever field you can take out, there is some kind of NP complete problem that comes out of it usually. So this is like the problem. Say, for example, now you want to convince, say P wants to convince B uh, that he knows the tree coloring for a particular graph. How he will go about doing it, right? So let's see this. So this is how it's going to work. So he will be like applying a permutation on the vertices. By that I mean like he will essentially just randomly shuffle the vertices order. So say if the vertex graph is originally represented V1, V2, V3, later it will be like V3, V2, V1 or some other order like right? It's just some randomly shuffle. And now so he will basically send that shuffled version, shuffled G. So let's call this graph, which for which he is trying to prove that he knows is here as G. So he will be sending a shuffled version of G to B. Okay, he won't be, there's no coloring in this, it's just that he will just say which permutation kind of, so it's something like that. So, and now, this we will be asking like, so mentioning two nodes, like I comma J. So send me the colors of this I and J node. And actually, I'm sort of made a mistake. Okay, I'll come to that. He will just send this I and J node, uh, and he will just send the color of this color of I from color of J, right? Okay, it's not the exact one is color of J. He's also sending the also sends the commitment of each of the colors for this one, right? As we saw before, commitment scheme like we can't know all the colors just by looking at the display.
So while suffering the graph, are we trying to preserve the vertices, the edges?
I mean, it's just like a relabeling. You can think of it as
Relabeling.
yeah, basically it's a relabeling. Yeah, so that's what it is. Yeah. So it's like so commitment of all the colors. It's like actually not one commitment. Technically, it's like multiple commitments. For our simplicity, can view it that way. Uh, so later when he comes in, he can use this and check like the prover is not cheating. Like this is like the CI and CJ. Yes, same as committed. So essentially, when he's sending this, he also sends how to open. He sends partial opening of this. So for I and J, he will send the opening of the colors. Can you see this okay, or I think I'll explain it slightly differently. So he sends like this shuffled version of the graph, and he sends like in each envelope, he just writes this particular node as this particular color kind of thing. So he just sends like say when there are n vertices, he sends such n such envelopes. Now when he asks I and J, he just opens that envelope corresponding to I and envelope corresponding to J. And now he will this verifier will check that these two colors are different. They are different, and as well as they are like the same, that they are coming from the opened envelope. They are not coming magically from anywhere else, but from the envelope. So that is all That is what the proof idea is. So let's see. Like in a graph, like say a simple graph, how many edges can be there? I think it will be like order of n square, right? Order of number of edges at least. It's a simple graph. So yeah. So the probability that he randomly pick, like say for example, if whoever is trying to cheat, he actually does not know what coloring is. He's trying to tell, he's trying to come up with something means. He can find that means there will be at least one place where the coloring is safe, right? So probability is like 1 over v or like 1 over v square. So with 1 over v square, this verifier will find something that will find some coloring which is this. So yeah. And you might be wondering why the shuffling the graph is important. It doesn't seem that important, right? Yeah. So firstly, let me do that because if we are only doing this thing once means there's quite a good probability. Like say if like the number of edges is 100, it's like the probability of finding this fault is like 1 over 100 square, 1 over 10,000 fingers. That's like not that good of catching a cheater. Right? So we have to do this multiple times to gain more confidence. So each time when we do, we have to sustain the differential. So that's why the shuffle graph goes in. So yeah, this like the cheating probability or like rather the non-cheating thing that is called the soundness. And the other property is like completeness. In logic, have guys have heard of like soundness and completeness? It's actually very similar to that. Completeness means that like for any graph instance, this protocol is going to work. So this is a complete thing, perfectly complete. It works for everything, and it's like probabilistically so because like, there is some tiny cheating probability. Even though you do it many times, you can't say it 100% guarantee like a mathematical proof that it is correct. But you can say it is very high probability. So this is like the thing. So this is like zero knowledge proof and idealistic. So there are like much more complicated versions in the way. This is like one of the first and simple things you see. Okay. Uh, okay. So let's come to one more last thing. This is like a bit of a fun thing. Okay, so this is called the dining cryptographers problem. This is like a toy version of what we do in general for multi-path computation. So in multi-path computation, usually as the name suggests, there will be like multiple different parties, right? Each party will be having like some input. Let's say the inputs are like x1 all the way up to xn. And now they want to compute some function, which is a function of all these things. You want to compute this thing. Right? But the point is that they should one way simple is like they can just send all the whatever the input they have to everyone and basically compute this thing directly. But the point is they should not reveal what their input to is to anyone else. But they want to this collective they can go with back and forth and things like that. I will take up a very particular example of this where the inputs and like this function f is also okay, so this is like the dining cryptographers. So like each one of these dots, imagine they are like a cryptographer and this circle kind of thing I have drawn here is a dining table. So what they want to know is like whether one of them has paid for the dinner or like the NSA. NSA is like American Secret Agency or something like that. I don't exactly really remember the abbreviation. So like NSA has paid for the dinner. Like in this thing, for simplicity, we'll be assuming like only one of them has paid for the nil, or none of them have paid for the nil. It's not like two of them can combine and pay for the simplicity of this. Or and when none of them have paid, the NSC has paid for the nil. The cryptographers want to come to know whether they have paid for the dinner or NSA has paid for the dinner. This is like the function they want to know. But the point is, they should not reveal to anyone else whether like one person can't say like if they have paid, I have paid. They can't say something like that because that would reveal who has paid for it. They should come up with a way to find this without revealing who has paid for it. Can you guys think of this? Can only one person. Either one person can pay, or one person has paid out of these cryptographers, or none of them have paid. If none of them have paid, the NSA.
Are we allowed to ask the initial and after state, after the writing state of theirs?
Uh, what do you mean, like how much money they they know those?
Yeah,
Yeah, and also don't think too realistically. Just think like they have like one bit of input kind of.
yeah,
That they have paid or not. So this is just like using that XOR kind of idea. So usually in these problems, don't just think of using the information that is existing there, but to generate more information by just using some random values. So, like, if we say like if they are paid, they take a one, they give a one, or if they are not paid, they give a zero. That they XOR it with some key which is known to them but not to others. But like if it's known to them, they can actually find who has paid, right? They should not know among each other who has paid. So randomly can configure pairs of two people the same key. Yeah, that's kind of the idea. You're very close to it actually. So like we randomly choose people to pairs of people who get the same key, and we just make so that they just XOR it with their key, and we finally just XOR it, all the values together. Yeah, yeah. To see one or zero. Yeah, sort of like that. Okay, so yeah, I will like explain a little bit more clearly. And okay, so this is the thing. So for each person, they have one person to their left and one person to their right, right? So they will like exchange some value. Let's say it's like V1 from here, and here it's like just say V1. Here it's V2, and these two exchange V3, and so on, right? Now each person without either like paid or not paid. If they have not paid, what they will do is like they will see who's on their left and what bit they have agreed on their right. For say for this guy, it's like V1 and V2. So he will just, because he has not paid, he will just say do V1 XOR V2. And he will just send that publicly here. So this value V1 XOR V2 is going to come here. So now these two people, say for this guy, let's say he has paid. Now he will send the negation of V2 instead of V3. He has paid, that's why he's negating it, right? Otherwise he won't flip that way. So this is like the thing he's sending. So similarly, all the parties will do this. In the end, they can like XOR all the results. If the result, if none of them has paid, you can kind of see like it will become zero, right? Because like each one will generate two times the very thing. Um, but if one of them has paid, because he has flipped it, it will be like one in it, right? So that's how this kind of works. This is kind of like the idea of MPC and things like that. Next, I will be talking about some of the techniques and things like that. So often what we do this, and this also relates to this NP completeness notion also, it is this notion of a reduction. So what this is what this reduction is. Let's say on this particular table there's like one cup and there's like a bottle of water down. Now if I tell you to fill that cup with water, what will you do? You just take it up, you just pour the water. Now I say that there's the cup and the water bottle is on the table. Now, how would you do it? You again pick it up and pour it in, right? This is like mostly what you do. But like mathematicians, what they usually kind of do is for the second case, they just say just pick that bottle up and place it on the ground, and now it has been reduced to a previously solved problem. That's kind of the so this is kind of the idea of a reduction. So you essentially reduce it to something that's previously solved, or like even if it may not be solved, it's some other problem. So you can kind of see a relation between them. This is essentially the kind of reduction. So for this NP-complete reductions, usually what they are called scarp reduction. So in this scarp reduction, what is happening is that okay, you will see more of this formally in the formal algebra, but like there's like a polynomial time algorithm which performs this particular reduction step. So that's kind of what the scarp reduction is essentially. So an NP-complete problem. Okay, how may I do that? You can. Oh. So an NP-complete problem is problem in which like there is this class called NP first. I'll explain what NP is first. So say for example you have a problem instance X. It's say described by n bits. So for example it can be like X is a prime number or a composite, or it can even be this graph coloring. It can be describing this graph or something like that. And there is something if it is like true. In this case, for example, you say for take this graph problem itself, like whether it's three colorable or not. So we have something called a witness. If it is like three colorable, you can give a coloring. That coloring is and witness that this graph is like three colorable. So yeah. So this witness size should be like polynomial in N, the number of bits wise. So this is like the witness. Um, so if you can kind of give this kind of witness and essentially verify in polynomial time that this witness, we can easily check if the coloring is correct or not in polynomial time, right? You just check all the pair of edges. It's quadratic color. So it's fine. So this is what a notion of NP is. NP complete problems are problems in NP such that all the problems in NP can be reduced to this problem. No, all the problem in NP can be reduced to this. So for example, this graph coloring problem is an NP complete problem, which means whatever problem in NP we take, let's say we're checking whether a number is prime or not, that is a problem in NP. That problem. So like if we have a solution to this problem, efficient solution to polynomial time solution to this problem, then we also have a polynomial time solution to checking primes or not, or some other problems and things like that. Like another problem is like SAT. I think you might have heard of like whether a proposition is like satisfiable or not. So like deciding this is like very inefficient. There's no known polynomial time algorithm. That is also another NP complete problem. So like yeah, there are more than one NP complete problems. Like these things are like reducible to each other and things like that. So yeah. So this is how it's like cryptography is also tied to complexity theory. In complexity theory as well, we use these kind of things, and this is how and this kind of reduction is used to work to improve in cryptography. Another technique that is used is like hybrid arguments, which are I don't want to go too much into detail, but you can think of like a space in which an abstract space in which each point is a distribution. And there is this thing called like the distances between two probability distributions. There are a few ways of measuring that. Like yeah, so arguing whether two distributions are close enough to each other or not. This is kind of like an example of hybrid argument and things like that. And don't worry if you don't get it; it's a bit of an advanced concept, and it may not be. And also another thing which is like very important in cryptography. Yeah. Other than we try to find the solution for this NP problem, if we can maybe find it with a probability of maybe around maybe 80 above 80% or something. Is that still NP or is that polynomial type problem? Uh, it depends. It actually varies to something like that. That's also what I'm going to come to now. Something similar to that. But for some cases, like for ET and things like that. Okay, for example, for this problem, the 3-SAT problem, which is you're given a propositional formula and 3CNF, and for that, if you want to know about more than 80 or not 80, I think it's 7 by 8, I think. Yeah, 7 by 8. Like if you if the problem becomes very easy because technically, so it's 3CNF. You understand, right? There are n clauses. So you're given some formula like this. CNF form. So each one it's or here, and there will be 3 things, and it's some variable, and it can be either normally appearing or negated and appearing. So this is what the TCNF problem is. So in this, okay, so each one of these kinds of things before which are appearing before an and is called a clause. So if you have generally given something with n clauses, there is always something which satisfies 7/8 out or 7/8 of n clauses. That's it, right? And it clauses means 7 times 7 by 8 times 100, and you take the floor of it. That many clauses can always be satisfied. So in those cases, you can just simply say yes and be done with it. So these kinds of results also exist. So I think I'm coming to it like this. And I will come to this thing. Say for example, we are talking about encryption, right? So I'll just come back to this again for now. Say for example, this encryption, let it be like a mathematical function, right? A mathematical function m comma like the message, and it's a mathematical function of simplicity, which means we are having the same message and the same key, we'll be getting the exact same ciphertext. Can you see some kind of problem will be eventually will be coming from this? Rather, I will be giving something another thing. For say for example, this M, let it be like a letter and message. Uh, for example, you are having a sentence means each letter A, B, or C, something like that. The same as. So then some letters in the English is more frequent E. Yeah. So you can just try to match the. Yeah. So that's the idea basically. So for example, if the same message will match to the same ciphertext. So if for example A occurs in this case and something is here, something is here, and A in this case as well, in both cases we'll be having some C, the same thing. So you can kind of match it, and you can easily figure out what the original thing is. This kind of thing is particular naive way of doing this is a bit problematic, and this is technically called ECP. You don't have to worry too much about it for now. Yeah. So this kind of thing is problematic. So there is also a field of cryptography, which essentially tries to come up with stuff like this. This is a very simple thing which I have chosen here. But in general, there are more things. So this thing is called cryptanalysis. So the meaning of it and breaking ciphers, there's an entire subfield dedicated to that. This is called cryptanalysis. And also to solve this particular problem, we don't have this encryption as a mathematical function. Instead, we have this encryption as an algorithm, technically a randomized algorithm. So what there will be is whenever we are encrypting it, there is implicitly like some randomness. So we'll choose some randomness and accordingly map it to the ciphertext. And this randomness will change every time. Like for each message, let's say this A, we will have chosen some randomness. For this A, we will have chosen some other randomness. If we can also choose the same thing, but that happens with like low probability and etc. So yeah. So whenever we are doing this cryptography, this randomness is like extremely important. How do we take care of it? I mean, even though if there are different randomness, there are ways of decrypting it. Like you can look into some schemes, like for example, there is this scheme like called Elgamal. This is somewhat similar to the discrete log based stuff, right? You can look into this particular scheme. It's quite simple. You can see how it things. You could also look into this. Uh, also look into the SNOT protocol or something. These discrete log based constructions are usually possible. So regarding this again reductions and things like that. For this like he asked like that, what if it's like 7/8 or something like that? But for some cases like we would just want to we don't need the exact answer, but we just need somewhat of a good approximation. Like for example, something like let's say okay, let me just take this graph coloring problem itself. And now this can be like kind of viewed as like coloring all the vertices as with three colors only, right? But I can kind of relax it as like what is the maximum number of vertices that can be colored only with three colors kind of thing. Like if you are choosing a subgraph and taking it in that kind of case, so how many things we are coming up with? So if we can say 90% of it, it's fine. In many cases, for applications, that's we don't have to find the exact three coloring. If even if we are able to color like 95, 98% of it and with three colors, it's fine. So yeah, those kinds of cases also exist. So yeah, so there are like different classes. Like this would be like something like this would be related to this application APX class. There are so many complexity classes and things like you can look into complexity theory, even there are things like this. And another thing I would say is like you can see how complexity theory and cryptography and things like this relate. For that, you can check this in clear. So the spelling is clear. Like INPAGLIAZZO. Yes. This is kind of like give you a good idea of like hardcore theoretical computer science and stuff. So yeah, so there are like many like beautiful connections between cryptography, approximation theory, and there are like these beautiful results like called PCP theorem and like things like this. So you can also see these connections as well. It's also connected to things like the unique game conjecture and things like that. So those are like very interesting open problems and you have to answer stuff. Yeah. And also, yeah, like here I was primarily talking about this discrete log problem and I was talking about these finite cyclic loops and things like that. We don't just use these things, we also use some that things. For example, we use something called lattices. And in mathematics, if you have heard of something like the sphere packing problem and things like this, sphere packing problem is basically like you are having like multiple spheres. It may be like identical or some different. There are so many variations of the problem, and then you just want to pack them as dense spheres, kind of things. These lattices and things like that are related to that. Uh, yeah. And also, if you have heard of elliptic curves, that is also getting used a lot. So yeah, so these kinds of things are like connections to mathematics as well as like this group theory. There are like many algorithms developed through theory and things like that as well. And for example, for if you have heard of something like RSK scheme, in RSK scheme we use these like prime numbers and stuff like that. So it's that way it's also connected to number theory and there's also things like that. As well as like for this thing, how do we know whether a number is prime or not, fast and efficient? There is something that, for example, for this commonly used is like I'm just giving names right now, not explaining much. There is this thing called the Rabin-Miller test for primes. So this is essentially what is an example of a randomized algorithm. Uh, a randomized algorithm is basically some algorithm which uses some kind of randomness. So testing whether something is prime or not, you use something like this. Usually. So yeah, I'm almost and also because yeah, as I mentioned, quantum computers, these lattices, these are like very commonly used. So like this RSA, this RSA relies on this factorization or this discretely. Quantum computers can break those things. But these lattices, they at least people believe the quantum computers cannot break these lattices based crypto systems. There are also many other systems like isogeny based and other etc. I don't want to go too much into that for now. So this is like the broad overview. And also if you have used any kind of like signature, like if you have seen something like SHA-256 and something like that, that is like a hash function and that is also related to cryptography. So that kind of thing is like used for like verifying the integrity of files. So if you have downloaded Linux ISO or something like that, you will have seen like SHA-256 and things like that. So, and just to know that essentially whether the ISO was not corrupted by the loading, things like that. And so, yeah, so there are like these digital signatures, like if you see on your web browser, there are these things called SSL certificates and things like that. They all rely on this digital signatures and stuff like that. And there is this MAC, and they can go on so much. Yeah, and one interesting thing is something called fully homomorphic encryption. Like usually in this thing, say if you want to perform some kind of computation, what we do is like they say you are having encrypted data, you have to decrypt it, apply the operations, and encrypt it again. This is like the typical way we do it. But instead of doing this, even for someone who does not have the capability of decrypting the thing, then they can directly perform operations on that encrypted thing. This is called like fully homomorphic encryption, or like there are some relaxed version of it. Those are just called homomorphic encryption. So it's something like if we know how to so like if we know how to encrypt it, so we might be able to do like operations on the encrypted state itself by trying to do another operation, which if decrypted will give you the original operation that decrypted state. I'll give you an example. Say for example, you have this encryption of M1 and encryption of M2. Let's say this you're the one who's encrypting it, and let's say what's your name? Yeah. So he's the one who's like capable of decrypting it. Like you can only encrypt, he can decrypt and encrypt, and I can't do like a kind of either of them. Let's say. But say you are encrypting this M1 and M2, and you're giving both these things to me. Now I want to come up with the encryption of M1 plus M2 means if I want to do this kind of thing, means I can actually do this. This is what fully homomorphic encryption enables me to do. And now, like, then I will be sending it to him. Now he can decrypt it, and he will be getting back M1 plus M2. And I'm just taking simple example of addition, but it's really any arbitrary expedition. So yeah. So these are like the main things, and also there is another thing like idea called that's like the final idea. So this is called oblivious. Let's say, for example, there's some kind of database. Let's say your college database. Say, for example, in that you just enter your roll number and you get how much marks you have scored or something like that. Now in a traditional database, like if you're doing something like this, that server, the database server will know like which particular student has queried because you're sending that roll number. So yeah, in some applications, we don't want that roll number to be also known to the database server. In those cases, we can use this kind of oblivious transfer kind of idea to come up with. And also in cryptography, we usually this is like a very useful method to get data and things like that. As well as, yeah, okay, one more thing. Yeah, cryptography, we typically like develop protocols. Like people develop for auctions, cryptographically secure auctions, communication, messaging, like WhatsApp protocols. There is like a secure protocol, Signal has almost like any application like Discrete or whatever thing you take, and they have all these things. So yeah, like currently I'm working on a protocol for like digital e-voting elections kind of thing as well. So yeah, that protocol development is like one of the important kind of day, kind of day-to-day things to do as well. So yeah, this is clear, right? Any question?
Describe what exactly is a hashing function, like a high level view of what it's supposed to be.
Hash function has actually this property is called properties pre-image resistance, which means that okay, so I just first write what the hash is. Hash function, let's say it's a hedge, and we take some kind of message, and it outputs some digest image. This digest is usually something like fixed size, right? Um, so this free image resistance means that just from this digest, the probability of you finding this m is like negligible. This is what the first property is. So I can essentially go backwards. This is what it means. Second property is second image resistance. So this means that since I'm having this x1 and x1 has this property that hash of x1 is equal to delta digest. Now given this x1, you can't find some x2 since that the hash of that is equal to the same digestance basically. So you can't find two things with this. Given that we have something. So this is like called that is this x2 is the second pre-image of this D. So coming up with this, the probability is also negligible. This is like another property. And the third property, which you might have heard, is like this collision resistance. Is this collision resistance? Collision resistance means is that basically if the probability of coming up with x1 comma x2 such that so x1 x2. So coming up with this both this x1 and x2 is like very small. So this is like the so and anything any function that like satisfies all these three properties is called like a hash function.
I think it's not necessarily a one-to-one function, but still I won't be able to find very easily two numbers
Yeah.
that can go to the same. Okay.
Usually these things are like technically like parameterized, like this security parameter which I mentioned, this lambda thing. So if it's like 128 bits, so it's like the probability of you coming up with this collision, you will take around per 2 to the lambda kind of thing. So it's like probability of that is like negligible. So that's what it
Thank you.
is.
Thank you, sir, for your talk.